So good afternoon, everyone. I know it's lunchtime, but let me finish this and I'll release you all. So my name is Bai. I am a PhD student at Phenolphthalein Research Group at Purdue University. I'm going to presenting today on the titanium dioxide-based surface treatment on concrete pavements for its potential in carbon dioxide removal and ability in self-cleaning. Bless you. So I'll be going over in the introduction for our project, our materials and method. We do the setting up for our experiments, and to test with it, the carbon dioxide removal and the self-cleaning, and I'll leave some final remarks. So we have known that the carbon dioxide emission has been increased for the past centuries, and if we look back into our concrete recipe, we found that in the production of the cement only, they contributed to around 8% of the total carbon dioxide emission annually. And if we account for the production of aggregates, we're looking for a much higher value. So how can we mitigate this? So one of these approaches is that we can develop some proactive sustainable properties that can actively absorb carbon dioxide from the atmosphere. So pavement as one of the civil infrastructures that can have a large amount of area exposed to the air is a great candidate for us to developing this kind of properties. So we know that the carbon dioxide sequestration in the cement-based material is called carbonation. It's mainly the cement hydration products react with the carbon dioxide in the ambient air and forms calcium carbonates, and this calcium carbonate will stay inside the cementous material. However, this is going to be a slow process. It's going to take decades to complete. Besides, it was also estimated that around 40% of the carbon dioxide we produced has been reabsorbed through this carbonation process. So one of these methods to increase the carbon dioxide uptake for us is to add the nano-titanium dioxide into the mixture. So besides the benefits that it can increase the carbon dioxide uptake, it also enhances some mechanical properties like the compressive strength and increase the durability. And this also brings us some photocatalytic properties. So in our previous research, we have some hypotheses that the acceleration of the carbon dioxide capture in case of the addition in nano-titanium dioxide to the mixture is due to the reduction in the crystal size CH, the calcium hydrate, and the increase in the pore surface area. However, this test, we did it when we add the nano-titanium dioxide into the mixture, but we are not giving up on all the existing pavement we have. So what can we do for the existing pavements? There's a commercially available titanium dioxide surface treatment provided by the Pavement Technology Inc. So they have this studied before for the asphalt and concrete surfaces, but these are mainly for the NOx degradation. So the company wants to know what happens to their photocatalytic pavements in case of the carbon dioxide. So this is our objective. So we want to assess the potential of the use of a titanium dioxide-based surface treatment to turn a concrete pavement into a carbon dioxide removal agent in an economically and technically feasible way. So let's move to our material section. We have costed 18 concrete samples according to the ASTM standard and the INDOT specifications for concrete pavement, and after that we cured them into the standard lab condition. For the titanium dioxide surface treatments, according to the manufacturer, the suggested application rate range is from 0.05 to 0.08 gallons per square yard. We have applied them for the minimum and the maximum application rate to see what happens in our samples. We apply the product to the specimen at a constant distance to make sure that the product is spread evenly, and we know that we know our area of interest, so we converted this application rate to weight gain in our concrete samples. After that, we cover the other surface where possible carbonation can occur and wait it to dry for 24 hours. So our method to do the carbon dioxide capture is that we have a seal chamber. Then we put our treated and untreated, titanium dioxide treated and untreated samples with a carbon dioxide sensor into that seal chamber. Then we turn on the valves and letting the carbon dioxide entering the chamber until 100% of carbon dioxide concentration is read by the carbon dioxide sensor. Then we can see that over time, the carbon dioxide concentration will go down. There will be 2 carbon dioxide exposure cycles for 3 hours of each, a total of 6 hours of exposure for each samples we did. And the sensor will recording the loss of the carbon dioxide in the chamber due to the sample's carbon dioxide reduction. So we get the raw data from the carbon dioxide sensor. It's recording the carbon dioxide concentration over time. And we used a linear regression method to record the starting value of the carbon dioxide concentration and the end value of the carbon dioxide concentration. We have 3 samples for each condition, as I said, the reference group, the minimum application rate, and the maximum application rate group. Then we take the average of this carbon dioxide reduction percentage as our carbon dioxide uptake rate. So this is our carbon dioxide reduction result for the first cycle. In fact, we can see that there's barely no significant difference between all the 3 groups. So the carbon dioxide can mainly be attributed to the carbonation in both treated and untreated sample. However, this carbonation is limited because it's actually consuming the cement hydration products, and after time it will finally stop. So this is our result for the second cycle. You can see that in the second cycle, the use of the maximum application rate surface treatment made a significant increase on the carbon dioxide reduction compared to the reference group. And if we put these 2 cycles together, we can see that in the reference group, the carbon dioxide reduction percentage is actually slowing down. And this is expected and reasonable because the carbonation is actually slowing down over time. And in the minimum application rate, we see that the trend is less pronounced. And finally, we see in the maximum application rate, the trend is even reversed. So the carbon dioxide surface treatment did enhance the carbon dioxide. The titanium dioxide surface treatment did enhance the carbon dioxide reduction. There are 2 possible explanations for that. One is if the carbonation is enhanced by our surface treatment, or there is a different mechanism is helping on the reduction of the carbon dioxide. So in order to know that, we did a phenolphthalein test. So phenolphthalein test is a test that we measure the carbonation depths. It's just we spray the phenolphthalein, which is a pH indicator on the freshly cut concrete sections, and we measure the carbonation depth measurement at the interval of 5 millimeter. So on the right hand side, you can see that this is our images for the phenolphthalein test, and you can barely see a difference in all the 6 samples. In fact, the carbonation depth is not really affected by the surface treatment. If we look back into our phenolphthalein test data, we can even see that in the maximum application rate group, the carbonation depth even goes down. So the carbonation is slowing, it goes down, but we have seen a more carbon dioxide reduction in our maximum application group. So the excess of carbon dioxide reduction within this with the surface treatment means that there might be a carbon dioxide decomposition is happening. So this is great because if it's decomposition, this might not be limited, and since the pH is increased, there might be no corrosion concerns. So one of the hypotheses we have is that this might be the carbon dioxide photoreduction. The carbon dioxide photoreduction has been studied for the titanium dioxide long before. It says that in presence of the sunlight and water, the carbon dioxide will form into the oxygen, carbon monoxide, hydrogen, and methane. So in our first cycle, we see that the carbonation is actually incomplete with the photoreduction activities. But in the second cycle, we see that with the carbonation slowing down, it is suggested that the photoreduction start to overshadow the carbonation. Besides, we know that the previous carbonation might also be positively influencing this phenomenon. As the carbonation is happening, the porosity in the surface layer is reduced, so that the carbon dioxide is hard to penetrate inside the cementous materials as it lives on the surface area and reacts with the titanium dioxide catalysis. Another test we did is the self-cleaning assessment. The self-cleaning assessment means that we want this ability to eliminate the pollutant without the use of work. It's one of the photocatalytic properties we have, and in order to do that, we do this according to an Italian standard, UNI 11259. So in the standard, it specifies that the slabs need to be sprayed with a pink dye. That's an organic dye called rhodamine B, and set to dry for 24 hours in a dark environment. After that, we start the UV light exposure, and we measure the color variation after 4 hours and 24 hours of UV light exposure. So in the UNI standard, it requires us to measure the color variation in the spectrum of LAB spectrum, color spectrum. So the A coordinate is the green to red axis, and we need to satisfy the requirement for a material to be considered photocatalytic if the changes in the A coordinate is over 20% after 4 hours and over 50% after 24 hours of UV light exposure. So a special photometer that measures colors, and it measures the colors in the LAB system. It's used for measuring the variations. So this is our result. We can see that both treated samples after 4 hours and 24 hours, they all met the photocatalytic threshold for being considered as a photocatalytic material. However, we are doing this on a rough surface, and we are also repeating this on a more smoother surface to see what the optical properties is also changing, and if this effect can be more advanced. So just give you a visual evaluation on the left side. This is a reference group that we didn't apply any titanium dioxide surface treatment. You can see that the pink dye is still remaining there after 24 hours. And on the right-hand side, this is samples with our surface treatment, and you can see that the dye is completely removed. So these are some final remarks. We did see that the titanium dioxide-based surface treatment enhanced the concrete carbon dioxide reduction ability, and the phenolphthalein test told us that it is not related to the carbonation, increase in the carbonation. It suggests a photocatalytic conversion of the carbon dioxide. So in the first cycle, we did see that the carbonation competes with the photoreduction abilities, but in the second cycle, we see that the treated samples showed a greater carbon dioxide reduction than the reference samples. So the carbonation in the first few hours might enhance the effectiveness of our carbon dioxide reduction. Is because the porosity in the surface layer is reduced, and it's letting the carbon dioxide staying on the surface layer, reacting with the titanium dioxide. The self-cleaning test tells us the treated samples all meet the threshold to be considered as a photocatalytic material. And part of this work has been submitted for publication and is currently under review. So in the end, I'd like to thank everyone from the Light Research Group. I would also like to thank the Frederick Andrews Fellowship for supporting me and Marina's graduate study at Purdue, and the Yale Fellowship, and the rest of the organizations for making me this trip to New Orleans.